why caffeine is indirectly linked to a reduced incidence of type 2 diabetes. There isn't anything directly linked between the two, it's all just indirect information. But if this happens to be extra credit, just a small little sentence describing how caffeine is related to type 2 reduced incidence of type 2 diabetes is fine. You don't have to give me an explanation for it. Just stating that is enough for that component. Okay? Question about the caffeine thing? Yeah. Caffeine is linked to a reduced incidence of type 2 diabetes. There's a bunch of theories why, but as long as you state that there's this link here, you'll be fine for the extra credit. So again, we see its particular role in this enzyme. You just have to state that there's a potential link between caffeine and reduced incidence of type 2 diabetes. There's something else I wanted to mention. Oh yeah. In order, if this happens to be your extra credit, and even if it's not your extra credit, there's could potentially be plenty of multiple choice questions describing, breaking down this concept here. And that is the phrase positive versus negative effectors and homotropic versus heterotropic effectors. Of these effector molecules we have listed here, glucose, caffeine, glucose 6-phosphate, ATP, and AMP, you need to be able to tell me whether they're homotropic or heterotropic and whether they're positive or negative effectors. So let's define each one of those terms here. The easiest terms to define, in my opinion, are what positive and negative effectors are. Yes, question?
Just a kind of random question about the diagram.
Mm-hmm.
Would you ever switch what side stuff's on?
He won't draw the diagram on there, if that's what you mean. If this is extra credit, you have to draw it yourself. If he asks questions about it, the diagram won't even be provided. You just have to kind of know it. Okay. So the easiest thing, in my opinion, to define first is whether an effector molecule is positive or negative, because it's simply the following. If an effector molecule is classified as positive, it is one that is activating the enzyme, the one that is pushing equilibrium to the more active state of the enzyme. If it is a negative effector molecule, reasoning is pretty obvious. If it's a negative effector molecule, it is deactivating the enzyme, and it's shifting equilibrium to the inactive state. So that's pretty easy. I'm not even going to write down those definitions. That one should be, you should be able to internalize that very easily. The others, not as easy. You see the phrase homotropic and heterotropic. So effector molecules can be homotropic and heterotropic as well. So what homotropic means is that the particular effector molecule you are talking about binds specifically to the active site. Okay, so homotropic means whatever effector molecule you're talking about goes to the active site. Heterotropic describes any effector molecule that goes to the not active site, meaning the allosteric site. Okay, so as simple as that. So because of this, these two different sets of vocabulary words here, you have four possible combinations. Regarding specifically for glycogen phosphorylase, only talking about glycogen phosphorylase, we're going to have to put these molecules here in their correct spots. So let's start with AMP here. AMP, is it positive or negative? Positive. Very obviously, AMP is a positive effector. It's shifting equilibrium to the more active state. So AMP is positive. AMP will go to the allosteric site, in part because AMP doesn't look anything like glycogen, so how could it even go to the active site? So AMP is a positive heterotropic effector molecule, so it's going to go in this box right here. Okay, so again, it's activating the enzyme and it goes to allosteric site, so it goes there. ATP is deactivating the enzyme and it goes to the allosteric site, so ATP is going to go right here. I'm going to skip glucose and glucose 6-phosphate for a second and just go straight to caffeine. Caffeine also doesn't look anything like glycogen, so it couldn't go to the active site. So it turns out caffeine is also going to go to an allosteric site, and it is inhibiting the enzyme. So caffeine is going to go right here. All right. So now what about glucose and glucose 6-phosphate? The substrate of this enzyme, of glycogen phosphorylase, is glycogen. Glycogen is composed of a bunch of glucoses. So therefore, glucose looks similar enough to glycogen that glucose and glucose 6-phosphate will actually go to the active site to try to deactivate this enzyme. Because of that, glucose and glucose 6-phosphate, because they go to the active site and they deactivate this enzyme, they're going to go in this box right here. Okay? So again, the reason why I'm going to put glucose and glucose 6-phosphate under negative homotropic is because they go to the active site to deactivate this enzyme, because they look similar to the substrate, which is glycogen. All right. This is every possible bit of information you could possibly be asked about regarding glycogen phosphorylase. If it happens to be your extra credit, I am pretty lenient when it comes to this stuff. Just drawing the diagram, unfortunately, isn't enough. You're going to have to provide short bullet point explanations. You don't need to give me long paragraphs. Just give me enough information that I know that you aren't cheating, that I know that you know what you're talking about. I will say, I'll take the opportunity to say right now, that grading the first extra credit, I can tell who cheated very easily. I can tell who stood in line and just asked someone, hey, what's the answer to the extra credit? Because your explanation had, I don't know how you got the answer, okay? So this one is going to be harder to do that, because look at all the information that could potentially help you out in terms of explaining this answer. I will be honest, you don't have to give me everything, but give me enough to tell me that you know what glycogen phosphorylase is and how it's regulated, okay? Everything here is the maximum bit of information you could give me, but just give me enough. Yes?
So, would you also want that chart at the bottom, the positive, negative?
It's up to you. As you can see, it's a lot easier to do it this way. I've had other students just write out AMP is positive, heterotropic, and each one what each one is.
So you would want that?
Yeah, either one is fine, but yes, explaining this is another bit of information that tells me you know what you're talking about when you're talking about glycogen phosphorylase. Yes?
You have to explain all of the box, like why.
Oh, explaining these? No, that's fine over here. As long as you tell me, homotropic means active site, heterotropic means allosteric site, like the basics here, that's enough for that. The most important stuff in terms of regulating this thing all has to do with the information up here. How is this thing covalently modified? Tell me what the enzymes do. Tell me that when you attach a phosphate to it, you're super activating it. Like the general, like the concepts that actually matter with this enzyme. There's a lot of details, as you can see, and obviously the class is only, 50, 60 minutes, because we give you a little bit of time. And I understand that when I grade this. Just tell me enough, show me enough that you are proving to me that you know what you're talking about when you're talking about glycogen phosphorylase. Yes?
Is phosphate a positive or effector?
Phosphate, not phosphate itself. So you're talking about like the phosphate up here or something? No, that's kind of like a different category of regulation for this enzyme. This phosphate is just specifically isolated to the covalent modification part of this enzyme. So we wouldn't use the term positive or negative effector here. Okay. All right, so this is one of your possible extra credits. When we get to 8A, I will show you the other possible extra credit question. And again, if either one ends up not being your extra credit, it could still end up being a bunch of multiple choice questions. So I'm going to move on. Okay. Other stuff regarding enzyme regulation. There are other ways enzymes are regulated other than covalent modification and allosteric regulation. There is something called Zymogen activation. When you go look in your notes, they give you 3 examples of enzymes that are regulated, that are activated via Zymogen activation. They will talk about insulin. They will talk about trypsin and chymotrypsin.
Is it pro or insulin?
It's the same thing, pro-insulin, insulin, it's the same concept. So insulin originally comes in a pro-insulin form, and I'll explain in a second what Zymogen activation means. So insulin, trypsin, and chymotrypsin, and blood clotting. Which I don't know the name of the enzymes. You don't have to know the names of the enzymes involved in blood clotting, just that they are activated through Zymogen activation. So what Zymogen activation is an enzyme that is activated through proteolytic cleavage. Activation through proteolytic cleavage, which is just a fancy way of saying you cut off a part of it in order to activate it. Proinsulin, you can find a picture of what that looks like in your notes. Proinsulin is a really long molecule, a long amino acid chain, and when you cut off a part of it, the regulatory part of it, whatever is left behind is the actual active form of insulin. So everything up here, and the enzymes and blood clotting, originally come in an inactive form. In order to activate any one of these things here, you cut off a part of it. That is called proteolytic cleavage. And then you've activated it. Okay? And that's about it for Zymogen activation. Regarding allosteric regulation, there's a couple other bits of information that are important. I talked about the general regulation via allosteric regulation through glycogen phosphorylase. So you should know, as a reminder, that the way allosteric regulation works, which is another way enzymes are regulated, all has to do with this equilibrium here between a relaxed and a tense state, right? The relaxed state is the active form of an allosteric enzyme, and the tense state is the inactive form. And so this equilibrium, this shift between one or the other, is what allosteric regulation fundamentally is. Kinetically speaking, you're going to see this shape regarding allosteric enzyme kinetics. Notice it looks quite different compared to the Michaelis-Menten kinetics graph. In this case, what this really means, what this shape means, well, I'll give you the shape term. They call this sigmoid. But what this basically means is that the enzyme exists either in an off state, which is indicated by this low line down here, and an on state up here. And there's a very small area here that shows this transition from off to on. This is a unique feature of allosteric enzymes, is that they are either going at maximum speed or completely off. That is what allosteric enzymes are, and that's what this graph is trying to illustrate for you. This sigmoidal shape is a description of that. So, I mentioned that allosteric enzymes have multiple active sites and multiple allosteric sites. This actually leads to a certain property regarding allosteric enzymes. Because they have so many sites, they are susceptible to a lot of different types of regulation. So allosteric enzymes are special types of enzymes that are very tightly regulated. Their activities are controlled by so many things that even just slightly turning it on or slightly turning it off is very tightly regulated. This equilibrium between active and inactive is very tightly regulated. Because of this very tight regulation of allosteric enzymes, very often allosteric enzymes you're going to find these enzymes at the very beginning of metabolic pathways. So allosteric enzymes are usually the enzymes that start a metabolic pathway. And we went over an example. We went over glycogen phosphorylase. It began the process of breaking down glycogen into glucose. So that was an example of the fact that allosterically regulated enzymes are usually at the beginning of a metabolic pathway. Oh yeah, these multiple active and multiple allosteric sites. I probably said it earlier, but I'll reiterate the next fact here. Allosteric enzymes are made of multiple subunits. Multiple subunits. Allosteric enzymes are very complicated in structure. They are made of a bunch of things put together. You can contrast that with Michaelis-Menten enzymes, which most of the time, I can't say all the time, but most of the time Michaelis-Menten enzymes are just a single subunit with one active site on it. Allosteric enzymes have multiple active sites and are composed of multiple subunits. They are a more complicated structure.
So are those like examples of isozymes?
Not entirely. Isozymes is a different thing altogether, and I'll get to that in a second. Actually, is that the next thing? One more thing and I'll get to isozymes. Alright, so that's what I have here for allosteric regulation. Moving right along. So of the ways that you've learned how enzyme activity is regulated, you've learned covalent modification, allosteric regulation, Zymogen activation, and there are other terms such as feedback inhibition or isozymes, which aren't necessarily the same descriptors as these, so I'll leave them separate and I'll talk about them in a second. But in terms of the main core ways enzymes are regulated, these are three of the ways that we learned about in detail. There is technically another way enzymes are regulated that isn't really talked about a lot, and part of that is because it's technically an exam 3 thing, but you will need to know a slight bit about it, and that is the fact that you can regulate enzyme activity by regulating the translation of the enzyme. So what this means, remember the enzyme is a protein. And you might remember from an earlier biology class, there's this thing called the central dogma of biology, meaning DNA contains the information that ends up eventually making your proteins. That DNA contains the information to make your enzymes. In order to go from DNA into a functional protein, DNA has to be transcribed into mRNA, and mRNA needs to be translated into an actual functional enzyme/protein. So the act of regulating the translation part of this is technically another way you can regulate enzyme activity. This is another way of saying just make less of the enzyme and you're slowing down enzyme activity. Or make more of the enzyme, you're speeding up enzyme activity. That is what it means when they say regulating the translation of an enzyme. It's just either make more of it or make less of it. That's how you can regulate enzyme activity as well. Of these listed things here, which one do you think is the slowest? Covalent modification is as soon as you attach a phosphate to it, you're done. Allosteric regulation is if the effector molecule is around, you're done. Zymogen activation is you cut off a part of it, it can go do whatever it needs to do. This one, you have to take the time to transcribe the DNA, for the mRNA to travel from the nucleus all the way to the ribosome, for the ribosome to translate that mRNA into an actual enzyme/protein, and for the primary structure of that amino acid sequence to fold in on itself to finally form a 3-dimensional version of the enzyme that can finally go do its job. The slowest way to regulate enzyme activity is very clearly this last one. Okay? Among these three, there's really a debate over which one's the fastest, so don't worry about that. Unequivocally, the slowest one is the regulation of translation of the enzyme. So, now going into 2 more little topics regarding chapter 15 that are important, and that is isozymes. Isozymes are a category of enzymes that it's the same enzyme, there's just different ways to make it. So the one example of an isozyme is lactate dehydrogenase. Which, depending on what version of it you have, on what isomer or isozyme that you have of lactate dehydrogenase, it may catalyze the reaction of converting pyruvate into lactate, or instead, it might convert lactate back into pyruvate. The reason why it has this dual function, this potential ability to catalyze each direction here, is because what an isozyme is, it's the same enzyme that can be that has multiple different compositions. I'm not going to draw out the diagram for this. You can take a look at the isozyme slide in your notes, but they describe that lactate dehydrogenase has 5 different forms that contain some combination of alpha subunits and beta subunits. Each of these 5 forms will contain a different mixture of alpha and beta subunits, and depending on how much of each it has, it may catalyze this reaction in a left to right direction or a right to left direction. You don't have to memorize which composition is which one of these here. You don't even have to memorize when it says in the notes which one is found in the heart, which one is found in the liver. Don't worry about that. What you do need to know is what an isozyme is conceptually. It is a special type of enzyme that can be made in different forms, and depending on which form you have, may catalyze a reaction in a different direction. Okay, so that's the very simple definition of isozymes there. The last bit is at the very end of chapter 15/13b, whatever that PowerPoint is. They talk about measuring enzymes in blood serum, right? Measuring enzymes in a blood sample, I should say. You don't need to know 99% of that for the exam. The most important thing that you need to know for that, and that part is what I said at SI, and I knew it was going to happen, is the simple fact that by measuring enzymes in blood, you are going to look for tissue damage, tissue and cell damage. So here's what that means. This is among the many different tests that they are performing whenever you give a blood sample at the clinic. They are looking for the presence of certain enzymes in the blood. And the reason why that is if you are detecting heart enzymes floating around your bloodstream, that's bad. It means that your heart is being damaged because your heart enzymes are supposed to be in heart cells, not floating around the bloodstream. If you, in a blood sample, you are detecting liver enzymes, that indicates liver damage. Because liver enzymes are supposed to be in liver cells, not floating around the bloodstream. That's the extent at which you need to know all that, like 2-3 slides of information there. Previous semesters, and maybe even for the final exam, I don't know. Right now for exam 2, I can tell you, you don't need to know the specific details of like lactate dehydrogenase ratios and liver enzyme ratios. I don't know. I can tell you don't need to know that for this exam. If it shows up on the final, I'll tell you about it when we get closer to the final. But for this exam, it's just this statement that matters. Measuring enzymes in the blood serum is important for diagnosing certain diseases. Yes?
Is that from the ALT?
Yeah, that section of the notes, ALT and all that stuff, creatine, phosphate, or whatever, I don't know.
So just that, okay.
Yeah, it's just this statement. It's the first, I think it's like literally the first sentence in that section of the notes there. Yeah.
So we don't need to know like where pyruvate and lactate are going to be found?
Oh yeah, the pyruvate lactate part up here, yeah, you don't have to know that for exam 2. If it shows up on the final, I'll talk about it when we get there. Yeah.
There was a slide after those, like a triumvirate or something.
Yeah, that is also more specific information that you're going to need for this exam specifically. Okay. So again, the most important part is this statement there. Okay. All right. And that is it for chapter 13b/15. Moving on to sugars. Let me make sure this is still recording. Okay. All right. A lot of this we actually happened to go over this week at the 2 SI sessions, so I'm not going to spend a lot of time on this because you can watch those videos, although there seems to be a problem with Monday's SI session uploading to YouTube. I'm going to try to fix that. But the most important bits of information here are you need to know the different monosaccharides that were talked about in class. You need to know the structures, what the following monosaccharides look like, what glucose looks like, which I will draw this one because it's the easiest one to memorize. So, monosaccharides are simple sugars. The most simple one and the most universally studied one is glucose because it's the most important one to us. Its structure is pretty easy. You have this nice cyclic six-membered ring. You have the CH2OH pointing out of it, sticking out of it, and you have these functional groups in an alternating pattern. Notice I have CH2OH pointing up here, and this adjacent OH here is instead pointing down. The one next to that one is pointing up, the one next to that one is pointing down, and this one is a special case. That alternating pattern you are only going to see in glucose. Note that if I flip this upside down, it is still glucose, okay? So don't, a very common mistake people do is they automatically assume, oh, CH2OH needs to be pointing up, otherwise it's not glucose. No, the key feature is this alternating pattern. That's the key feature that tells you have glucose, yes?
If it's not flipped by CH2OH down, so we
If CH2OH is going to be pointing down, this one better be pointing up. And that alternating pattern is the important one. So as long as whatever position each one is in, as long as you have this alternating pattern, you are talking about glucose. Okay. This special carbon here, and this is again me slightly jumping around because we're getting to certain bits of information. Oh yes, question.
What if they were like all flipped, almost like a
If everything was flipped, so good news, you won't be asked to visually identify which enantiomer you're talking about. And I'll explain enantiomers in a bit. So really, if they were all flipped, it actually would still be the same version of glucose. Like if this one was pointing down and this one was pointing up and this one was pointing down, this one was pointing up, it would still be the exact same version of glucose because enantiomers are harder to illustrate in the cyclic form. So you won't have to worry about enantiomers in the cyclic form. Okay. So this is the start of the chapter 7 stuff. So again, I'm jumping around a little bit because of what we draw. Right here, since we're at the topic, is a special carbon called the anomeric carbon. Every sugar has an anomeric carbon somewhere. What an anomeric carbon is, it's an oversimplification, but what an anomeric carbon is one bonded to two oxygens. Okay? This is the only carbon in the entire structure that's bonded to two oxygens. You should look carefully. A lot of people think that this one is bonded to two oxygens. That's not true. The only one that's bonded to two oxygens is this one right here. Because of that, it gives it some unique properties. The functional group right here, this OH attached to this anomeric carbon here, whenever you have a hydroxyl group attached to an anomeric carbon, we call that a free anomeric carbon. Okay? And it really, really only has to do with whether there's a hydroxyl group attached to this spot. So if your sugar, whether monosaccharide, disaccharide, or polysaccharide, has a free anomeric carbon, that functional group can flip upside down, right side up, in all different directions here. What I mean by that is this functional group can undergo mutarotation, which means it can transition from something called an alpha anomer to a beta anomer and back freely without changing anything really significant about the name of this monosaccharide. In other words, if I flip this up or down, it will still be glucose. Okay? If I flip anything else on here, if I take one of these other functional groups and I flip it around, it will no longer be glucose, it will be called something else. But if I flip this one either up or down, all I am changing is whether it is the alpha or beta anomer of glucose. So let's talk about that right now, whether something is alpha or beta anomer. Okay, so I've drawn both possible anomers of glucose. We can check that this is still glucose because these functional groups here are alternating positions. Up, down, up, down. Same thing over here. Up, down, down. So it is still glucose. The way to identify quickly whether you are dealing with either an alpha anomer or a beta anomer is just checking which direction the anomeric hydroxyl group is pointing and compare it to CH2OH. I'm going to highlight those things right here. If they are anti to each other, if the hydroxyl group on the anomeric carbon is anti to the CH2OH, this is your alpha anomer. If they are pointing in opposite directions, that is your alpha anomer. Now, this is true for monosaccharides, disaccharides, and polysaccharides. Okay? Just take a look at the anomeric hydroxyl or whatever either OH, OCH3, or glycosidic bond goes here. You compare that to CH2OH and it'll tell you what type of anomer you have. And this over here, because they're anti to each other, it's an alpha anomer. Everything else, as in if they're pointing in the same direction, is your beta anomer. So that's how you quickly identify which anomer you have for a monosaccharide. After glucose, actually, since I talked about free anomeric carbon, I forgot one very important term here. If whatever sugar you're looking at has a free anomeric carbon, you can call it a blank sugar. What? A reducing sugar. So let me write that down here. If you have a free anomeric carbon, you can call that sugar a reducing sugar, meaning it can participate in oxidation reduction reactions. It's just a phrase that is used to describe that. And only sugars, whether monosaccharide, disaccharide, or polysaccharide, only ones with free anomeric carbons are able to do this. So if they ask a question is X sugar a reducing sugar, it's just a fancy way of asking, does it have a free anomeric carbon? Okay. All right, so let's talk about anomers.
That is oxidized.
Yeah, it's able to participate in oxidation reduction reactions, but even that's more than what you need to know. It's more the phrase that's more important, is the fact that it is a reducing sugar. Other than glucose, you need to know 5 other monosaccharides. There's one that he gives you an acronym for, Galloman. I'm not going to draw these, but their structure should be very easy to identify, because they look exactly the same as glucose. In fact, to save time, because it allows me to explain this next thing. Here we go. All right. So here's glucose up here. I know it's glucose because up, down, that alternating pattern. And take a look at this acronym of Galloman. The first one here is galactose. If you compare it to glucose, you'll notice it only differs at exactly one spot. That is this functional group on the left here. Okay, that is the only hydroxyl that's pointing in the opposite direction compared to glucose. Everything else is the same. Allose, instead of the carbon on the left there, is the carbon right here in this second position here. The hydroxyl is pointing in the opposite direction. And finally, mannose looks very similar to glucose as well, except this last carbon right here is pointing in a different direction. That's how you can easily memorize the structures of these sugars. Is once you know glucose, you now know galactose, allose, and mannose. There are some terms you can use to describe these sugars to each other. We mentioned already enantiomers, okay, and I talked about it at SI as well. Enantiomers won't be asked to identify their structures, but conceptually what an enantiomer is in this context is. If I have D-glucose, the enantiomer of D-glucose is L-glucose, okay? That's it. I don't have to know what L-glucose looks like. I just need to know conceptually that L-glucose is the enantiomer of D-glucose. There are other phrases, such as diastereomer, epimer, and anomer. We already went over anomer. Anomer is really easy. Anomer is you just look at the anomeric carbon and you figure out whether it's the alpha anomer or the beta anomer and you're done. So we're left with 2 other terms, diastereomer and epimer. What does each one mean? Diastereomer, the definition, if 2 molecules are diastereomers of each other, it means they differ at least 1 chiral center. They differ at least 1 chiral center. What that means is, if I compare glucose and galactose to each other, They differ at exactly this carbon, one of your possible chiral centers here. The hydroxyl is pointing in different directions at that chiral center. Everything else is the same. So glucose and galactose are diastereomers of each other. They differ at least one chiral center. What about galactose and allose? If we compare galactose and allose to each other, are they diastereomers of each other? Well, let's see. This carbon on the left is definitely different between galactose and allose. And this second one right here is also different between galactose and allose. They differ at 2 chiral centers. They are diastereomers of each other. So in order to determine whether 2 monosaccharides are diastereomers of each other, just look at their functional groups and what direction they're pointing in. If they differ at least one spot, they are diastereomers. The last term to talk about is the phrase epimer. Epimer is a more specific type of diastereomer. So in fact, if you got multiple answer choices, and one says diastereomer and one says epimer, make sure you're picking the most accurate answer choice. So I'll explain why that is. An epimer is a special type of diastereomer that only differs at exactly one chiral center. Okay, so an epimer is technically a diastereomer, but is more specific and more limited because the definition says they differ at only one chiral center. We'll give an example here. Galactose and glucose are epimers of each other. They only differ at this one carbon, at this one chiral center on the left here. But would you say galactose and allose are epimers of each other? No, because they differ at 2 places. Differing at 2 places allows you to call galactose and allose diastereomers of each other, but because they differ at 2 places rather than 1 place, you cannot call them epimers of each other. Okay, so that's and I'll summarize again those terms. Enantiomers, the only time that's relevant is if you're talking about D sugar versus L sugar. Diastereomers, as long as they differ at least one chiral center, they are diastereomers of each other. Epimers, if they differ at exactly one chiral center, they are epimers of each other. And anomers, you have to look at the anomeric carbon and figure out if one is an alpha anomer and one is a beta anomer. Yeah.
So all the Gallman sugars are epimers of glucose, but not each other.
Exactly. That's a good point that you bring up. Each of these Gallman sugars are epimers of glucose, but if you compare them to each other, you can only use the phrase diastereomer because they differ at least 2 chiral centers. Yes, question?
So what if you had like alpha galactose and alpha allose, then wouldn't they be epimers?
Alpha galactose and alpha allose would differ at 2 spots. You'd have to draw it out, but alpha galactose and alpha allose would differ at this carbon on the left and this second one right here. They'd be pointing in different directions, so they'd be diastereomers. Yeah.
Is there a reason Alice doesn't have like deuterium or whatever that is on that?
Yeah, I don't know why it does that. I think he just pulled it off something in Google Images, so don't worry about that. Is this running out? So yeah, the squiggly line, by the way, you may not get that on the exam. That is just for your notes to illustrate that the squiggly line represents the anomeric carbon. So go with the way I taught you guys to identify anomeric carbons. Just look for the one bonded to 2 oxygens. Okay. All right, let me make sure I covered all of what I wanted to cover there. Okay. One more thing regarding these structures here is, remember how in exam 1 you were asked which carbon determines whether you have a D amino acid or an L amino acid, right? And that was the very central carbon, that was the alpha carbon in an amino acid. You may get a question, given a picture of a sugar, which carbon tells you whether you have a D sugar or an L sugar? The simple answer is the second highest numbered carbon. Okay? Today at SI, we talked about how to number carbons given a monosaccharide. I'll give you a short explanation of that here. How do I know what numbered carbon each of these carbons are? Remember in organic chemistry, you had to number carbons based on where certain functional groups are, right? You wanted your alcohol carbon to be as low of a number as possible, and then you count from there. Same rules kind of apply here. You want to number your carbons where the most oxidized carbon is as low of a number as you can make it. The reason why I say as low of a number as you can make it, you'll see when we get to fructose. So let's look at glucose here. My most oxidized carbon is very easily identified as the anomeric carbon because it's attached to two oxygens. This one I'm going to call carbon 1, and I'm going to number all the other ones to make sure I cover all of my carbons. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6 is the one sticking out of the sugar. The one that determines whether you have a D sugar or an L sugar is the second highest one, in this case, carbon 5. It'll be a different carbon for ribose and a different carbon for fructose, but for glucose, galactose, allose, and mannose, it is carbon 5, the chiral center at carbon 5, that tells you whether you have a D sugar or an L sugar. Note that you do not have to identify given a picture, you do not have to identify given a picture whether you have a D or L sugar. You just have to know which carbon on there tells you whether you have a D sugar or an L sugar. Okay? For contrast purposes, let me try to find a picture of fructose. All right. Let me zoom in here. All right. So fructose here is a 5-membered ring. Okay. Fine. Okay. Fructose here is a 5-membered ring. It still has 6 carbons in them. We need to find which one on here may potentially be the anomeric carbon, and what numbered carbon is the one that tells you whether it's a D sugar or an L sugar.